Hi everyone, I'm going to tell you about our work verifying instruction selectors in production compilers. The context of our work is compilation in security critical contexts. That might be a JavaScript or WebAssembly engine in a browser, or in the cloud and a function as a service platform. These environments use JIT compilation for performance and rely on sandboxing for security. But a compiler bug could be escalated by malicious code to allow sandbox escape and stealing data. So security depends on compiler correctness. Formal verification offers a solution, and CompCert has achieved a fully verified compiler. However, that was a great human effort. So the techniques aren't mainstream in compilers like Clang and GCC, and a focus of our work is how we can use formal verification selectively to improve the security of production compilers. Our work focuses on Cranelift, which is a compiler that backs the Wasm-to-native WebAssembly runtime, and it's used and trusted by major companies. In addition, we focus our work on a particularly vulnerable stage of compilation, which is instruction selection, that bridges a compiler's IR down to target machine code instructions. This can be simple, where a single IR instruction maps to a single ISA instruction. But a lot of the complexity in production compilers comes from the fact that the selector performs a wide array of peephole optimizations in which sequences of IR instructions are mapped down to selected ISA instructions. Not only that, but single IR instructions can contain a lot of embedded logic. For example, this signed division requires an entire sequence of instructions to do required overflow checks. And I'm sure you can see that there's a bug in this one. This one, we'll talk about later, wasn't security critical, but other bugs have been, where some of the worst vulnerabilities in Wasm-to-native have caused critical CVEs, and the root cause was an instruction selection bug. We'll make this concrete later, but we'll think of instruction selection as a graph, where IR nodes enter on the left and are ultimately rewritten to ISA nodes. But crucially, this happens via a sequence of intermediates, which are governed by instruction selection rules. And prior work has taken the natural approach of verifying this rule by rule, where developers can handwrite specifications for the nodes, and the verifier can confirm that the edges preserve behavior. However, in production compilers, these graphs are huge. This is the graph for the ARM backend in Cranelift. And that brings us to our first challenge, which is that with prior approaches, we would need massive annotation and specification burden to reach full coverage. Not only that, but we don't just care about verifying pure computation. We also have to reason about side effects, because these instructions may load and store from memory, or they might trap in exceptional circumstances. And prior approaches have dealt with this by modeling the entire state of the machine and carrying around an entire representation of the memory array, for example, is bloated and causes inefficiencies at scale. Lastly, modern ISAs are huge, and instruction selectors target a significant subset of these instructions. We need to know their behavior, so we have to specify the semantics of many machine instructions with intricate behaviors. If you do this by hand, you're likely to get it wrong. So that brings us to our work in Arrival, which is an instruction selector verifier for Cranelift that allows end-to-end verification with high assurance and reduced effort. And we do this with a few techniques. We introduce rule chaining that allows us to reason about entire paths through this graph at once. We introduce a lightweight state modeling method, and we automatically derive our ISA specifications from vendor-provided semantics. And with all this, we're able to verify nearly all of this ARM backend required for compiling WebAssembly core instruction set. And we'll focus on a couple of these techniques with the rest in the paper. So let's take a look at how Cranelift achieves instruction selection. It manages complexity with a domain-specific language called ISLE, in which developers write rules consisting of a left-hand side pattern, and on a match, it will rewrite to an expression. So what we're looking at here is a match on IABs, or integer absolute value instructions, on types 32 bits or less. And on a match, it produces this ABS node on 32-bit operands with sign-extended inputs. But in fact, there's two rules one for the 32-bit case, one for the 64-bit case, and they both use this same helper. So you can see how this graph begins to form. But in fact, it continues, because this abs helper is implemented in terms of a compare immediate and a conditional negate, so the graph gets a layer deeper. But we're not done, because in fact, this compare immediate is implemented by emitting the lowest level machine code IR in the compiler. And we see the same on the bottom. So actually, even in quite a simple case, instruction selection is implemented by the interaction of multiple instruction selection rules. And as I said, prior work introduced a specification syntax that allows developers to define the behavior of each of these nodes and verify that the edges preserve behavior. So we could take that approach here, right? We could verify all the edges by specifying the behaviors of all the nodes. But that brings us back to our challenge of scaling to the full instruction selector. And that's the motivation for our rule chaining technique. The idea here is, what if we could reason about an entire path through this graph at once? And Arrival allows us to do this. It is able to compute the composed effect of all the rules along a path and verify that the entire composition preserves behavior. On top of that, we have an algorithm that can enumerate all viable paths through this graph. And this helps us achieve our goal of reducing specification burden, because developers are only required to provide specifications at the beginning and at the end. So that's the idea, but in practice, in these production graphs, there's complications, that there are cycles, which mean that in practice, there are infinitely many paths through the graph. There are also high-degree nodes, as well as common helper nodes, which might have a low degree but appear frequently, which means that if we apply this technique in an unlimited fashion, we would hit path explosion. So the insight of rule chaining is that we can gain most of the benefit by applying this technique within subgraphs. And Arrival provides control to the developer by placing intermediate specifications, as well as annotations to control the use of rule chaining. And the result is that we can avoid specifications on most intermediate nodes while keeping this path explosion in check. So that's how we deal with intermediate nodes. We still have this challenge of specifying the behavior of all of the ISA instructions we're targeting. There are many of them, and they have intricate behaviors. And we handle it by auto-generating them. Thankfully, in recent years, processor vendors have begun to distribute machine-readable formal semantics of their ISAs. This was led by ARM, but we believe that Intel is following suit pretty soon. Doesn't this just solve our problem? The answer is not quite, that these semantics they distribute target many use cases, and as a result, they are very verbose, and they contain low-level details not required for user space or compiler verification, as well as all possible processor variants, which means that they are actually notoriously difficult to use. Thankfully, recent prior work, a project called ASLP, which actually featured in this conference already, solves this by partial evaluation. It is able to take a concrete instruction on the left and produce a succinct semantic program describing its behavior. However, we're still not quite done for the domain of compiler verification, because we don't actually have a single concrete program that we want to reason about. We need to reason about entire families of programs, or more specifically, we need to know the behavior of this machine code IR, which itself covers millions of possible concrete instructions. So that is, we need specifications for symbolic machine code. The observation that we make in Arrival is that, in fact, fields of this IR map naturally to bit fields within the encoding. And we leverage this to build a pipeline for specification generation. Starting with a family of machine code IR instructions, we were able to represent this as sets of symbolic encodings, where each one has partially fixed bits and partially variable ones. On top of that, we forked and extended the ASLP project such that we can generate semantics for these symbolic encodings. And then given such a semantic program, we can convert it into IL specifications to use in our verifier. And with that, we were able to auto-generate almost all of the ISA specifications that we needed for verification, replacing thousands of lines of code that would otherwise, or producing thousands of lines that would otherwise have to be written by hand. So with that, we were able to use our verifier to verify almost all of this ARM backend required for compiling the WebAssembly core instruction set, totaling over 6,000 rule chains. And doing so with reduced developer effort, where of all of the nodes that are encountered in this verification scope, 60% of them benefit from some form of arrivals automation, be that terms that don't need specs at all because of chaining, or a large number of them that we're able to just auto-generate through this ISA specification pipeline. And it's viable for introduction into production workflows, where a continuous integration run of this verifier takes 11 minutes and covers almost all of the scope. And lastly, returning to this sign division bug from the beginning. This is a bug where an overflow should have been caught, but wasn't because of a miscompilation. Arrival is able to catch complex bugs like this, which required analyzing 12 IL rules in combination. It required modeling state, particularly traps and flags, and it required intricate specifications for 7 different ISA instruction families. So with that, I've presented our work on how we scaled verification to production instruction selectors, and thank you.
Thanks a lot. Any question? Yeah.
Hi, thanks for the nice talk. Have you checked the soundness of your encoding of your semantics for those instructions? Like, did you find any bugs in your encoding? Because you are basically reinvented new semantics for all those instructions.
Do you mean, did we find any bugs in ARM's specification, or did we find?
No, you use this ASL to generate the semantic from the symbolic encoding of your instructions. So is that, how do you know that the sound?
Okay, so we do have to trust that our translation is correct. We did find some bugs in the process. We found some bugs in Cranelift's assembler itself through this process. And we did find some bugs in the prior handwritten specs that we were using. Okay. But we do have to trust that the translator from ASL into our language is correct.
Okay. Have you dealt with any instructions that need to deal with concurrency? How complicated is that?
We haven't. So do you mean things like atomics? We haven't covered that. Yeah.
Okay.
Yeah.
Thank you.
Okay, next question.
Thank you for the good talk. In the CI slide, you mentioned you achieved 97% coverage or something.
Yeah.
I wondered if you can talk quickly about what's left. Is it timeouts, or is there some technical limitation?
Yeah, it's timeouts. So the verifier is SMT-based, and it struggles with all the things that SMT often struggles with. For example, large divisions, multiplies, and remainder operations, as well as some of the large population count instructions sometimes timeout. So yeah, the things that aren't covered in that verification scope, they do get covered if you run it long enough. But we think there's value in the CI environment in covering most of it, right? Yeah.
Thank you. Please thank the speaker again. And